So, quotient groups and homomorphisms. We learned about the quotient group, how you form it. Given a normal subgroup n of G, then we can construct a quotient subgroup by using concepts. Okay, now we want to see how the quotient groups relates some properties between normal subgroups and then the quotient groups. There are some properties related between them and homomorphisms. This is what we are going to do in this lecture. So relating quotient groups and homomorphisms. Okay, so we start with the following definition. It says if f from G to H is a homomorphism of groups, then the kernel of F is the set A belongs to G such that f of A equals the identity. Okay, so let me write that clearly. F is a group homomorphism that goes from the group G to another group H. Okay, so let me represent it here. This is the group G, assume, and this is the group H, and F goes from G to H, and it is a group homomorphism. A group homomorphism, remember what a group homomorphism means. We have f of A B equals f of A f of B, and here we abbreviated that the operation between A and B is the operation of G, let me write here, but the operation between f of A and f of B, let me write it this way, which means the operation of H, and these elements indeed A and B for all elements A and B that belongs to G. So this is a quick recall for what homomorphisms mean. That means if the function f is distributed over the elements. Okay, now what's happening here in this group H? We have an identity, and we denoted E of H. So some elements will go under F to the identity. So we will collect the elements whose image are the identity. All of them goes to the identity. We collect all these image together, and we will call it. See, I'm choosing elements from the group G such that the image of any of these elements will go to the identity of H. So I'm collecting them in one set, and I will call this kernel of F. Sometimes we use the parentheses or no. So this is the kernel as we defined it here. This is the kernel of the function f. So this is the kernel. It is a very important definition. It is a very simple set, but it is very important definition. Actually, we have seen a motivation for defining a subgroup to be normal. We wanted to achieve some property that we call the star. If A and C are congruent modulo K, B and D are congruent modulo K, then A times B is congruent to C times D. We called it operation star, and that was the motivation to define a normal subgroup. Actually, another motivation to define normal subgroups is the kernel. The kernel as a set, it is a subgroup and it carries some property, and we use that property to give a definition of normal subgroups, but we will not be doing this here because we have already defined what normal subgroup means. And now we will show that the kernel of any homomorphism is a normal subgroup. The kernel of any homomorphism is a normal subgroup. So before we do so, we will just go and work on some examples to get familiar a little more with kernels. So let's take the function f, the homomorphism that starts from R0. Remember, R0 is the group of all non-zero real numbers, all the real numbers except the zero, and the operation is multiplication. And F goes to R double star. R double star, remember, it means the set of all positive real numbers, and the operation is multiplication. And this map is defined by f of x equal x square. Now the question, is that a homomorphism? Let's see, this is f of a times b, so which is a b all square, and then it is an abelian group R star, so it's a b, so it is a times b, so it is a square b square, but a square is f of a and b square is f of b, so we got f of ab equals f of a, f of b, and therefore this is a homomorphism. So what is the kernel of this homomorphism? The kernel of f, will be all the elements in the domain, which is the set of non-negative real numbers, such that f of a is 0. But what is f of a? F of a is a square, so we need a square to be 0. So we are looking for real numbers that whose square is 0, and we only have the 0 in there, right? The only number you square, you get 0. The only number you multiply by itself, you get 0, is the 0. Okay, so kernel f here is just consists of the single element, which is 0. Notice here, kernel is not empty. Kernel f is not empty.
Doctor,
go ahead.
it is 1 or 0.
Huh?
It is 1 or 0. I think it is 1.
Oh, sorry. I'm thinking, but I have something. Okay, I was thinking something wrong is happening here. Okay, so let me complete that. Thank you. It is the one. The identity is 1 in here. I was thinking 0. So kernel f is not phi, since why there at least there is one element. There is one element that goes to the identity of H, which is the identity of G. So that means we will have element, the identity of G belongs to the kernel, and the identity exists, and therefore again let me emphasize that and write the kernel of any homomorphism will never be phi. Okay, thank you. In here I was thinking that like something wrong is happening here, because if this function is not 1-to-1, so the kernel has more elements than this. But this has been taken care of because the domain, the codomain of the function, which is the range here, is the set of positive integers only. So let's see, the identity here is 1. So let me emphasize that somewhere here to the right, the identity of R star of R double star is 1, the one we know, the regular number 1. So the kernel here consists of -1 plus 1. This is much better, yes, because what I was thinking here, that the kernel shall not consist of one element, it shall consist of more than one element. If the kernel consists of one element, then that element is the identity of the group in the domain. And when this happens, then the homomorphism is 1-to-1. We will see that in a theorem in a little while. But f of x equals x squared is not 1-to-1. So when I put 0 in there and then I got the kernel to be 0 only, like I stopped for a while. Was something wrong happening? So thank you for bringing my attention here. The identity is not 0. The identity is 1. So the kernel here consists of 2 elements. So let's go and compute kernels of more examples. Okay, let's go here. Now the map is from the group R star cross R star, so the domain consists of ordered pairs. Zero is not allowed there because we are crossing non-zero real numbers with itself. And the domain here is R star. So it takes an ordered pair. So what does F do for an ordered pair? It will just send it, we'll do like this, it will send it to the second component. So this is a projection. It will send it to the second component. And it is trivial, but I will leave it to you to prove this map is indeed a homomorphism. Okay, so again, what is the identity here? Before we keep moving, the identity of the codomain is 1. So we want to see what elements goes to 1. So okay, let's have a look at it here. So the kernel of F consists of ordered pairs A, B that belongs to R star cross R star, such that the image of that ordered pair, what is the image of that ordered pair? So let me write all these things in detail so that the image equals 1, which is this identity. And that means it is the set of ordered pairs that comes from R cross R, such that, well, the image of this element is B itself, such that P equals 1. Oh, interesting. So we will take all that pairs that has second component to be 1. So the kernel is A and 1. Okay, such that A belongs to R star. So it is the all ordered pairs, okay, that has 1 as second component. And remember, A first component is not allowed to be 0. So if I want to draw that to just understand, to make a visualization of what that means, if we take this to be x axis and this the y axis, and then the points in here, what are they? We go to y and fix y to be 1. So here we go, this is 1, and then we take all the points on this line, all of them, infinitely many of them. So this is the kernel, and we did not take the point 0, 1 because we are not allowed, because 0 is not in R star, so A cannot be 0 here. That means A cannot be 0 between parentheses. Okay, so this is the kernel of this homomorphism. So let's keep going and compute the kernel of this homomorphism. F goes from Z to Z5. It takes an element to its equivalence class. Remember that it takes an element to its equivalence class, and here we have 5. So for example, f of 13 equals what? The equivalence class of 13, which is what? The same as the equivalence class of 3. Okay, and so on. Now, what is the identity of Z5? This is Z5 again. The identity here, the identity of Z5 is just simply the equivalence class of 0. But we know that the equivalence class of 0 is the same as the equivalence class of 5, or I mean the equivalence class of 0 consists of all multiples. Well, so we have enough information actually to write it more directly. The equivalence class of 0 consists of all integers that are divisible by 5, or all multiples of 5, which we know and we have seen before. It means 5z. Okay, so this is okay, this is the identity of Z5. So the kernel here, the kernel of F, consists of all integers A belong to Z, such that the equivalence class of A is the same as the equivalence class of 0. which means all integers in Z such that A belongs to the equivalence class of A is the same as 5Z. That means A belongs to 5Z, which is simply now so this looks very similar, 5Z. Okay, so the kernel is a subset, actually it is a subgroup of the domain, and the domain here is Z, so the kernel came out to be 5Z. Here, if you notice, I am using this notation. Maybe I'm abusing this notation. Maybe I should stick that Z5 to the definition. I should stick myself to the definition. Z5 equals, just we made a convention about that, 0, 1, 2, 3, and 4, and that's it. And then I will say the identity is just the equivalence class of 0 or just 0. So I can take this off if I wish, or if it is confusing you. Okay, so in general, actually, let me go to the side in here. We have seen such examples before, and I want to generalize that. We have seen a generalization of this map F is from Z to Zn, defined by f of A equals the equivalence class of A. And now you know the kernel of F consists of all multiples of n, which means it is nz. So this is a generalization of the example we just have seen. Okay, now so far we defined what is a kernel, what is the kernel of a homomorphism, and we want to prove it is a subgroup, and it is normal subgroup. So let's go for it. Let H be let F from G to H be a group homomorphism with kernel K. Now we are using K to denote the kernel of F, so that we use easier notation. Then K is normal subgroup of G. Okay, so we need to prove first K, the kernel is a subgroup. So first K is a subgroup of G, and to prove it is a subgroup, we need to prove the identity is in there, and we have already done that. So the identity of G belongs to K. Why? I will write this again. Since the image of the identity of G, this is G, equals the identity of H, and why this is true, since F is a homomorphism. Okay. Now we want to prove that let A and B be two elements. Now to complete the proof that K is a subgroup, we want to show that AB inverse also belongs to K, and that will give us K a subgroup of G. So let's do that. How we prove that this thing is in J and K? How we prove this thing is in the kernel? Any element is in the kernel if its image is the identity. So actually, let me rewrite that again in green. So we want to show that f of AB inverse is the identity. Once we do this, that means AB inverse is in the kernel. So let's work it out. So let's see, f of AB inverse, we have F a homomorphism, so we can do this. Now since F is a homomorphism, then we know that f of an inverse of an element is the inverse of the image of that element. I mean, we can rewrite this the following way. This is F of B inverse. Okay, because F is a homomorphism. In general, if we have F to be a homomorphism, we know this. This is happening. We already have it in hand, right? So, okay, Since A and B are in K, and K is the kernel, then their image is the identity. So this equals the identity of H, and this equals also the identity of H. Now take the inverse of the identity is the identity itself, and then we are done. We started with the image of A, B inverse, and we show it is the identity, so this is true. Then we are done. Now it remains to prove that K is normal subgroup, is a normal subgroup, and we will do it this way. Now we want to say K is normal in G. How we do it? So we want to show that A inverse KA belongs to capital K for all elements in the group G. Remember that K is a subgroup of G, and all elements small k in the subgroup itself. So remember, this is how we prove that a given subgroup is normal. This is one way. So A inverse AK, this is a small k, and this is a big K. So we want to show that. Okay? But what does that mean? K is the kernel. So to show something is in K, we need to show that the image of that something is the identity. So let us write again what we want to show. Want to show that f of A inverse times small k times A equals the identity of H. Is that easy? And the answer is yes. Now let's see. We have f to be a homomorphism, and that will help us a lot. So this is f of A inverse, f of k, and f of A. So we distributed f over all these elements, but we know also that f of A inverse is the same as f of A inverse, and this is f of k, and this is f of A. Okay, now we want the result to be the identity. Now this equals, let's see now what's happening here. Okay, now okay, now where's small k is from? Small k is from the kernel, right? And so f of k is the identity of H, because this element is from the kernel. So this one equals the identity of H. Now what we have here, f of A inverse times the identity times f of A. So we have the inverse of f of A times f of A itself. So we have the element f of A times its inverse, and we are in H, and therefore this shall give us the identity of H. So what we have proved that the image of A inverse KA is the identity, which means that we proved that A inverse KA is in the kernel. So the kernel is not only a subgroup, but it is also a normal subgroup. So write that down in your own language. Say the kernel for homomorphism is a normal subgroup of the group in the domain. So the kernel of a homomorphism is a normal subgroup. Oh, okay, now you know, if I give you a subgroup and tell you, okay, prove it is normal. How you do it? You say A inverse, say the subgroup is N. So you will say A inverse in A is contained in N or belongs to N. This is how we prove a given subgroup is normal. But now here we are gaining a new way to prove that a given subgroup is normal, and this way might help us at sometimes. Simply show that that given subgroup N is the kernel of some homomorphism. And we know the kernel of any homomorphism is a normal subgroup, so that subgroup is normal. So we will apply this method here in this example. Now, this example says take a homomorphism, take a map from Sn to Z2. What this map do, let me write it here. It takes from Sn the group of permutation, the symmetric group of permutation, and it goes to S2. Look in here you have a lot of elements and factorial elements, but in here you have only 2 elements. And what does this F do? It takes a permutation sigma, and it will tell you, okay, if sigma is even, then I want the result to be 0. Okay, because you know this group consists only of 0 and 1. And it says if sigma is odd permutation, then we want the answer to be 1. Now, prove that F is a homomorphism. So I will leave it to you to prove that F is a homomorphism. And actually this is because when you multiply 2 permutations, both of them are even. So you have a permutation that can be represented as a product of even number of transposition, and this also can be represented as even number of transpositions. Multiply them together. What you do, you just order or arrange the transpositions here and here and make them look like they multiplied by each other. Don't multiply them, just list them there, and then you will count the number of transpositions that you have. You already have even in here and even in here, so you have even plus even, which is even. So the multiplication of 2 even permutation is even. What about the multiplication of an even permutation and an odd permutation? For the even permutation, we have even number of transpositions. For the odd permutation, we have odd number of transpositions. When you multiply these permutations, what you do, you just list the transpositions of this one and this one to next to each other. So don't do multiplication, just list them in there. So you will have even number of transposition plus odd number of transpositions. So the result will be odd number of transpositions, because we know that even plus odd gives odd. So the result of an even times an odd permutation will be an odd permutation. For the same reason, think about that the product of 2 odd permutations will be even permutation. That's because odd plus odd give us even. And this, what I said, is what shall help you to prove that this map is a homomorphism. Okay, what do we want from this map? We want the kernel. So which element goes to the kernel? To 0. So what is the identity of the group in the codomain? It is the 0. Okay, so which permutation goes to 0? Oh, they are the even permutation. So we will write here that kernel of F is the set of even permutation. It is simply an. Oh, great. Therefore, by the above theorem, we have that an is a normal. We know it is subgroup, but now it is a normal subgroup of Sn. So you see how we concluded that? Because an is a kernel of some homomorphisms which starts from Sn. Okay. Okay. So the very first result that we will achieve from the definition of the kernel is the following. This is a very interesting theorem, very intuitive and interesting one. It says that if we have a homomorphism F, let me write it here, F from G to H. This is a group homomorphism. So let me write, it says homomorphism of groups. Okay. And we are saying here with kernel So let me take it to this side here. Okay, more. Okay, with kernel F to be K. Okay, now what does this theorem says? It says that if we find that the kernel consists only of the identity of G, we know the identity is in the kernel. Okay, there might be other elements that are also in the kernel, but we are saying here, if there are no element, or if there is no element in the kernel rather than the identity, then that means the homomorphism we are working on is injective, is one-to-one. So good. If I ask you to prove a homomorphism is injective, you may go and compute the kernel and prove the kernel consists of the identity only. Then that means the homomorphism is injective. And the opposite way, if we have a homomorphism in hand which is injective, then we know that there is nothing in the kernel except the identity. So let's prove this theorem. So let's go for that direction, which means assume K consists of the identity only. Now we want to prove F is injective. How we prove a given element is injective is one-to-one. We assume there are two elements that have the same image, and then prove these two elements are essentially the same element, they are equal. So suppose that f of A equals f of B for some element AB in the domain of the homomorphism. So that means f of A times f of B inverse will give us the identity of H. But that means, since F is a homomorphism, this is f of A B inverse give us the identity of H. And that means now this element here has an image which is the identity. So this element belongs to the kernel, but the kernel contains no element except the identity itself of G, which means A inverse B must equal the identity of G itself, because we have no other element. Well, that means that means B inverse is A inverse. Well, and that means A is B. And we are done. And so F is injective. And that gives F is injective. Okay, now let's prove the opposite direction. Let's prove the opposite direction. Let's prove this direction here. We assume F is injective and prove that the kernel consists only of the identity. What we do here, we will say, okay, assume we have an element in the identity, and then we force that element to be let's assume there's an element in the kernel, and then we force that element to equal the identity. This way we show there is no element in the kernel except the identity. And okay, so let's do it. Assume okay, so let me start with the hypothesis. Assume F is injective, and we have F is a homomorphism here. So I will say here, suppose F of A equals the identity of H for some A belongs to G. Okay, and what that means now, so F of A is the same as F of E of G. Why is that? Because E of H is the image of E of G, right? Now what we got here, we got two elements, A and E of G, whose images are equal. But F is injective. So how could this possible? So we must have A to be the identity of G, and does that look like G? Oops, what I do? Okay. Identity of G, and that means a kernel consists only of the identity. The kernel of F consists only of the identity of G. Okay. Okay, so every normal subgroup is a kernel. Okay. Now, we said a little while that if we have a kernel, then it is normal subgroup. But what if I have normal subgroup in hand? I can show you that originally this normal subgroup comes out as a kernel of some homomorphism. Okay? So with these two results, the ones we have already and the one we are going to prove now, theorem 8.18, it says that normal subgroups are equivalent for being kernel. So normal subgroups come out of kernels. So okay, let's see. Let N be a normal subgroup. We start with a normal subgroup of G. Then the map, we are defining a map here from G to G factor N, the quotient group, this way. Then this map is surjective and the kernel of this map is N. So this looks like very trivial, like we are cheating ourselves. What we are doing here, we are sending a map G to G over N. Okay, so this is the map phi. So what does that do? It will take an element here. Okay, where does it send an element? Well, it sends it to its own coset, right? So we have a group G and then a subgroup N. Then we will take an element of G and we'll say, okay, you go to it, to your coset, please. You go to your coset. Okay. Now the question here: which element goes to the coset N or NE? We know that. Okay, I must make that clear. We know that the identity of this group of G factor N, we have seen this before to be in itself, or in the coset of N, or the coset of E, the coset of N with respect to E. So let me drag this here, which is in itself. Remember that we will need it later in when we go to rings and ideals. So the identity of the factor group, you know, the factor group consists of cosets. The elements in there are cosets. So the identity is one of them. Which coset is it? It is in itself. Now I will tell you why I said we are cheating here. It says the map by, it takes A to its coset. So the question here, which elements go to the coset N, the identity? Well, they are the element of N itself. So the kernel here is in itself. So this is what we are saying. The kernel of phi, which elements goes to the identity? They are the elements of N. So let's prove that. Let us prove it is a surjective homomorphism. So let's prove it is a homomorphism. We have seen this before. A homomorphism hereby is a homomorphism. I think we have seen this before. Let's see how we do it. If we have bi of AB, that means N, the coset of NAB. Yes, we have seen this before. But that means N of A times N of B. And N of A is bi of A, and N coset of B is bi of B. So it is a homomorphism. Is this surjective? Bi is surjective. Let's prove it. And we are cheating here again because we are sending an element to its coset. So if we want to show it is surjective, just go and pick some cossets and then find an element that goes to this cosset. But we are sending elements to their own cosset. So take that cosset and take element from inside it and then send it back to there. So that's the element you have taken from inside it is the preimage. So let me write that. So let's choose an element. So let me do it some way. Let X is an element in the group in the domain. That means X is some cosset, right? For some A belong to G. Now by of A is an A, and it is X. So what we have done in here, we have chosen an arbitrary element in here, which is a cosset, and then we found an element whose image is that cosset. It's just simply G over N here, set of cossets. So you want an element to go to a specific cosset, take an element from that specific cosset and then send it back. Okay, now what's about the kernel? Let me do this in red. What is the kernel of pi? Simply the kernel of pi, according to the definitions, are elements inside the group G such that pi of that element is the identity. What is the identity? It is an E, which means, so what does this equal? So let's rewrite it again. So let me give it another color. What does this equal? So this means I want to pick elements from G such that an A equals an E. Well, an A and an E are the same cosset, which means A and E are congruent modulo n. Correct? And we have seen this before. When we say an A equal an E, this is equivalent for saying, okay, let me write this in more general. Let me write it here. When we say an A equals an B, two elements are congruent modulo subgroup. That means A B inverse belongs to N, right? Remember this? Now this goes for B here. So we have A E inverse belongs to N. Oh, what does that mean? But this means A is in N. Oh, okay. Now, so the kernel is, rewriting this, A belongs to G such that, so I will replace all this by what I got here. So this is equivalent to that. So I will replace it. I say A belongs to G such that A belongs to N. Well, this is cheating. But what that means? So that means it's N. A belongs to G such that A belongs to N. This is N. So the kernel is N. So the theorem is proved. Okay. Now we have the to prove, okay, one more thing to prove the first isomorphism theorem. We have a very fundamental and important theorem in abstract algebra, and which is called first isomorphism theorem. And there is a second isomorphism and a third isomorphism theorem. What we will see today is the first isomorphism theorem and the second isomorphism theorem. And to prove the first isomorphism theorem, we need this lemma. We need this lemma. And this lemma is interesting. I can see all theorems here are intuitive. If you have if you have a good grasp of the ideas of cossets, and when two cossets are equal, what that means for their representatives, and what does it mean for two elements to be congruent modulo a given group. If you have a good grasp of these ideas, then the theorems we are seeing today will be trivial for you, almost all of them. Now let's see what this says. If we have a homomorphism again, F from G to H, and K is the kernel, so I would like to write that K is the kernel of F. Okay, K is all elements that goes to identity, or element that goes to identity. Okay. Now what does this says? Now if we have two elements A, B and G, then these two elements will have the same image under F, if and only if they are congruent modulo K, or they give you the same coset, if they are representatives for the same coset. And this is very interesting. Do you know why? When if I want to write something here, assume we have an element, we'll be finding ourselves using that. Assume B equals K and Ka, where K is in the kernel. So I want you to think about it this way. Now B consists of K times A. When we upload B inside F, so F is a function, it is a shuttle that takes B to its image. It is the same as taking Ka, because B is Ka. When we are going inside F, the small k will disappear because it goes to the identity. What I'm saying here, f of B is f of K times A, right? But this is a homomorphism, so this will disappear. This will be identity. This will be identity. So we will have here f of A. So f of A equals f of B. What we assumed at the beginning, we assumed B equals Ka. Oh, how is that related for B and A to be congruent modulo K? So this is the idea of the proof. Actually, I would like to make it more fun. If you want to understand the spirit of these things. Okay, now what's happening here? Let's see, this is G, this is H, and F is a homomorphism from here to here. Now choosing an element here, I make it big. Under F it will go to somewhere. Now what F will do, it will take that element and it will clean from it any parts that comes from the kernel. So it will take the element, it will clean the parts that comes from the kernel, and it leaves a part which is not from the kernel, and then take the image of that part. Okay, and this is what happens here when we talk f of K times A. It cleaned K and left A itself. Okay, so I wanted you to see it, to think about this intuitively, and this is the idea of the proof. Actually, this is how on which we will construct the proof. So we will prove this direction. Assume f of A equals f of B. What do we want? We want this to happen, right? We want Ka to equals Kb, right? Now this is the subgroup. It's not a small k, it's a big K. Okay, so but tell me how we do so, how we improve this thing, how we prove that two elements give me the same coset, which means two elements are congruent modulo that group, right? So I want to prove this. If I prove this, then we are done. Oh, okay, but what does that mean? Remember, K is the kernel of F, right? So I want to show that the image of this element is the identity. Oh, okay, it's easy. We have done this before. So f of A B inverse, since F is a homomorphism, is f of A times f of B inverse, right? Oh, okay, but we have f of a2 equals f of b, right? So f of b all inverse is the same as, so let me rewrite this, f of a. So I will replace that by, because f of b is f of a, right? Okay, so f of a times the inverse of f of a, and that equals the identity, and then we are done. Okay, let's prove the other part. Let's prove this part now. Assume we have ka equals kb. What that means? They are, a and b are congruent modulo k, right? Oh, what does that mean? K is the kernel. So let me write this here. So the image of AB inverse, because AB inverse is the identity. Oh, okay, but we know that this equals f of A times f of B inverse, and this gives the identity of H. Again, we know that this here in red equals this. All right, and so what we get, f of B, okay, sorry, so what we get in here, f of A, so I would write f of B here. Now notice f of A times inverse of some element is the identity. So what we get in here, so simply we will get, okay, literally writing this literally, that means f of A inverse. Because we're multiplying f of A by something, then we get the identity. Then that something is the inverse of f of A. Oh, that means simply f of B is the same as f of A. And that's what we wanted, right? Because we proved from here to here. So this proof is done. Now you may write it in your own words. Two elements will give the same coset of the kernel if they have the same image. Now let me give a demonstration for this theorem. I'd like you also to visualize the theorems. Okay, these theorems they are new for you, and then you will have you need some effort to put them together and comprehend them and get them in hand. To do so, you need to demonstrate them in some graph. You make some graph that helps you to understand this theorem more and get used to it, or write them in your own words in English or in Arabic. Anyhow, and for myself, I will show you how I graph this theorem. I have a map from G to H, okay, and that map is homomorphism. So I will write here, I did not write it before, so this is a homomorphism. Okay, now it says, well, okay, it says I have two elements here, A and B, okay, and it says A and B goes to the same place in here. They are equal, they have equal images. So that means now go back to G. Remember when we factored G as, when we partitioned G as the set of coset. Remember Lagrange theorem, where G equals the union of the cosets, and the intersection of any two cosets is phi. Remember the theorem which says every two cosets, they are either the same coset, or they are disjoint. So remember that what I will do is I will partition K according I will partition G according to the cosets.
Hi.
To our demonstration of this theorem. So partition G as cosets of K. So I will do this for K, and maybe this is another another cassette, say it is KC, and maybe this is another cassette in here, K and D, and in here is another cassette, K and H, wherever, and in here is another cassette, K and E, let me say K and whatever, G. Okay, now what this theorem says, if you do this, so then you will find that A and B are coming from the same cassette according to this partition. They cannot come, each one of them come from a different cassette. Okay, they will not have the same image. If they come from different cassettes according to the kernel, we are talking about the cassettes of the kernel. If they come from different cassettes, their images are not the same. If their images are the same, then that's because they are coming from the same cassette. They are giving the same cassettes. Okay. The first isomorphism theorem. Okay, so it says if we have a homomorphism again and again, F from G to H, which is surjective homomorphism, and K is the kernel, then the quotient group J over K is isomorphic to H. This is a very, very important theorem in algebra at all levels. So what does it say? It says if we have a G and then a homomorphism, F is surjective homomorphism, and it goes to H. So all H is engaged, so I mean surjective. Now the kernel, we are assuming here the kernel K is the kernel of F. Okay, now what's happened here, we are saying the quotient group G over K is isomorphic to H. So let me write that. G over K is isomorphic to H. Actually, what is happening here, let me move this from the way. And emphasize somewhere that K is the kernel here. K is the kernel of F. Okay, so what's happening here, if we make another diagram here for J over K, the factor group. So what's happening, we made a partition of J as cassette of A, but if we go this way and represent each of these cassettes with some representative, so this is KE, so we will say this is KE, and this element is A, for example, so this is KA, and so on, KC, and so on. Now what's happening here, we will take that KA to, so again let me write this, make my diagram a little clear. This is the cassette KA represented by some element A. We will take it, we will create a map and take it to where? To F of A. Now what's happening here? We had A here. What we have done, we taken A to its own cassette, as we have done a little while ago, from G to G over N. Now it is from G to G over K. Once we done that, we took the cassette to the image of A. And remember, A goes from here to here directly. Take A under F to its image. There is a direct way. This is a direct way. Or go the other indirect way. Take A to its cassette. Take A to its cassette. And then take that cassette to the image in here. So actually, what I am saying here, if we take, we will move KA to F of A. You know what? Because I just said that if we have k an element from the kernel multiplied by another element, then simply this will go to the image of that element, and the part k in here will disappear because it goes to the identity. Okay, so this is a diagram that helps you to understand the first isomorphism theorem. Now our goal here is to prove this isomorphism. So how we prove that two groups are isomorphism, isomorphic? We just define a map between them and show it is an isomorphism. So it is from J over K to H. How we define it? J over K, this is J over K here. It consists of cosets. Okay, so this map phi will take elements that are cosets to the images of these elements. Okay, so it will take a coset K of A to the image of A. Okay, because remember H is the set of images of, so it is the set of images of elements that are coming from J. Why? Because F is surjective. Okay, now we will prove that phi is surjective. So phi takes K of A to F of A. So to prove it's surjective, let K B belongs to to prove it's surjective, we want to choose an element from H. So choose B belong to H. What we want to find the coset that goes to H. Simply take that coset to be the coset of B. So we chose an element from H. I want to show it has a pre-image as a coset. So the coset of B is okay. I must use one step before that. Sorry. So let's go back. Since B is in H, since B in H and F is surjective, so I need all this. Okay. Since B is in H, then there exists A belongs to G such that B equals F of A, right? This is because, let me write it in here, because F is surjective. Any element in H will has a pre-image in G. Okay, now what we do, we want to show phi is surjective. Now, and phi goes from G over K to H, and then we chose an element in H. We want to show there is a pre-image for it inside G over K. Now take phi of Ka. So I got the coset here. It is Ka, and simply by definition it is F of A. And what is F of A is B, and then we are done. Okay. Now to show phi is injective, so we will assume that phi of Ka equals another coset phi of Kb, and that means phi of Ka is A, and phi of Kb is B, F of B. And this is according to the definition here. But we just have proved that by the previous theorem. We have just proved that if two images have the same, if two elements in the domain have the same image, that's because they make the same cosets for the kernel. So that means K of A equals K of B, and then we're done. With here we assume that phi of Ka equals phi of Kb, and we proved Ka equals Kb, and that proves phi is injective. Now to prove phi is a homomorphism, let's do it here. To prove phi is a homomorphism, so we will say, okay, let's say we have phi of Ka times phi of kb. So we need to choose two elements. Remember, phi goes from g over k to h. This is where phi goes. Okay. Okay, so it's that equals, because of the definition of coset multiplication, a phi of kab. But what is phi of kab? It's f of ab according to the definition, but that means it is f of a, f of b, because f is a homomorphism. But what is f of b? F of a. F of a, actually now we go the opposite way. This is phi of ka, and this is phi of kb. Now what we have done here, phi of ka times kb is equals to phi of ka times phi of kab, and therefore phi is a homomorphism, and that gives now this phi is an isomorphism, and g over k is isomorphic to h. This is the first isomorphism theorem, and it is a very important theorem in algebra. Okay, let's work examples on that. Let J and H be groups, and F is going from G cross H to G, and F is the projection on the first coordinate. So F will take that to the first coordinate in here. Now the F here is surjective, and you know it is homomorphism. We have just seen like this, and it's left exercise for you. So it is a homomorphism and surjective. And what is the kernel of F? The kernel of F consists of elements in the domain, but they are ordered pairs, such that the image of this, what is the image? The image is the first coordinate equals the identity of H. So kernel of F consists of all elements whose first coordinate is the identity and second coordinate is an arbitrary element of H, and this is simply the identity. This is, sorry, the identity. Okay, the identity of G here, I shall say the identity of G. So this simply consists of all it consists of all ordered pairs whose first coordinate is the identity of G and second coordinate is any element in H. So it is a cross product between this trivial group, which is the identity, and the other group. And therefore now, by the first isomorphism theorem, we will write it this way. We will have that G over H over the kernel, which is this, is isomorphic to what? Is isomorphic to what? What is the image in here? To G. Is isomorphic to G. Okay, good. If you look at it here, it looks like we are doing cancellation. Like if we cancel this and this, we get G over the identity, which is G itself. If you would like to think about that, if we take the normal group to be only the identity and factor G over N, then we are actually doing nothing. We are taking cosets of the identity. So each coset will consist of one element only. So this is actually isomorphic to N itself. So we will do it, write it this direct way. This is isomorphic to G. I'm sorry, G, not F, not N. Okay, another example, the function that goes from the set of non-zero complex number to the set of positive real numbers, and the map takes a plus bi to a square plus b square. This is for people who know complex numbers. So the kernel here, the kernel of F, will consist of a plus bi such that a square plus b square gives 0, and a and b are real numbers. So if we add two squares, we get 0. A square of any real number is positive, so we have the positive number plus positive gives 0. So we only have one choice. So the identity is 0 plus 0i. We must have a and b to equal 0. So the kernel here is that. So the complex numbers factor group over the identity, which is the complex number itself, as we have just seen here above here. Any group factored by the identity is the group itself, but by the first isomorphism theorem, this is isomorphic to the group in the image, because we did not mention that this is surjective homomorphism. So this is by first isomorphism theorem, we get that. So the complex numbers are isomorphic to the group of positive real numbers. Okay, let's see this example here. It takes okay, we have just seen it before, right? The kernel here, we have seen that the kernel here is 1 and -1. Okay, and now by and this is surjective. We have seen it is surjective homomorphism. So by the first isomorphism theorem, we will have R star quotient group where the subgroup is -1 and 1. This is isomorphic to R double star. Okay. So again, if we have a homomorphism, then take the domain, homomorphism which is surjective, take the domain and make a factor group of it over the kernel. That will give us an isomorphic group to the group in the image. Okay, so remember that I would like to emphasize it. If we have F from G to H, which is a surjective homomorphism with K equals the kernel of G of F, sorry, then G over the kernel. So let me write it with this kernel. G over the kernel is always isomorphic to H whenever we have surjective. All right.